Hello everyone, I'm Zhen Rong from Xi'an Jiaotong University, and I'm excited to present RELIA, Accelerating the Analysis of Cloud Access Control Policies. This is a joint work with Huawei Cloud. We all know that modern infrastructure is built on the cloud. To secure this infrastructure, companies use complex access control policy, or ACPs, to define who can access what. The problem is, these policies are often written by developers, and mistakes can lead to major security breaches. A simple typo could make sensitive customer data visible to the public. To prevent this, we use automated ACP analyzers like AWS Zelkova. They work in three main steps. First, they convert the human-readable policies like this into formal SMT constraints. For example, a policy allowing access from some user becomes a set of regular expressions on a string variable. Next, they add an intent, which is the security question we want to ask. We can manually specify who can access which resources like this, but recent works has also presented some automatically analyzable intents. Finally, they feed all these constraints into SMT solver to get a definitive set or unset answer, which tells us if the policy violates our security intent. But there is a bottleneck. The process is slow. ACPs heavily rely on regular expressions over strings to define roles and resources, and SMT solver struggles with these string constraints. In our test with real-world policies, these three timed out after 3 seconds on 26% of the queries, and 4 more complex synthesized policies, leading solvers like CVT5 failed to return an answer even after hours. Why is it so slow? So at their core, SMT solvers tackle string problems through a process that is fundamentally a search. They try to construct a string that satisfies all the conditions. To give you an idea of the scale, the number of possible 5-character string is astronomical, far more than we can ever hope to enumerate. While solvers use heuristics to prune the search space, the complexity of regexes means that the search often explodes. This leads us to the key question. Since we all cared about is whether a string matches a set of regular expressions, so do we need to really reason about the strings themselves? Our key insight is no. We can partition the whole entire infinite universe of strings into a finite number of string equivalent classes, or SECs. The rule is simple. Any two strings in the same class behaves identically with respect to all the regular expressions in the policy. For example, consider these two regexes from the policy. They split the string space into exactly 3 equivalent classes: strings that matches neither, the ones that matches only the first, and the one that matches both. Instead of reasoning about infinite strings, we can now reason about just the 3 classes. This is the core idea behind our tool, RELIA. We designed RELIA to be a transparent preprocessor, and it sits in between the analyzer and the SMT solver, which is why we use the coffee grinder analogy. The analyzer produces whole beans, the hard string constraints, and RELIA grinds them into fine grounds, simpler integer constraints. And the SMT solver, our coffee machine, can process much more efficiently. This design makes RELIA agnostic to the specific solver and analyzer being used. It simply transforms the problem into an easier one. So, how does this grinding procedure work? Let's walk through an example. Notice that this is only just a very simple example, and real policies are much more complicated than this. First, RELIA computes the SECs from all regexes in the policy. It is done by an iterative process of intersecting and subtracting the regular expressions in the constraints. And then we label each SEC by a number like this. Each string variable, like user, is replaced with an integer variable, which represents the SEC number it belongs to. Then we rewrite each regular constraint. This constraint is true for strings in SCC1 and SCC2. So we replace it with the LIA constraint here, user equals to 1 or user equals to 2. We do the same thing for the not constraint. Notice that we only transform the str in RE part. The logical structure, including the not, is preserved for the solver. Finally, we add a range constraint to ensure that the solver picks a valid class. The hard string problem is now a simpler integer problem. Another crucial challenge we handle is concatenation. Cloud resources names are often built by concatenating variables like semester plus a slash plus row. Raleigh uses a novel FA algorithm to correctly and efficiently propagate regular constraints on the concatenated string back to the component variables. This is a very complex topic, and we invite you to see more details in our poster session and in our paper. So, how well does it work? We evaluate Raleigh across 3 dimensions. For real-world policies, we tested on over 500 policies from Huawei Cloud on 2 kinds of analysis. We plot the speed of Raleigh on logarithm scale over the original solver's time here. Raleigh achieved an average speed of over 8 times compared to the best of using STRAY3, CVC5, and CVC4 directly. And for more challenging policies, we crafted 10 of them that are effectively unsolvable for standard solvers. Raleigh solved 8 of the 10 policies in under just 3 seconds. Raleigh can also solve general string problems, and still faster than STRAY3 and CVC5. To sum up, analyzing cloud access control policies is crucial for security, but it is often interactively slow due to the difficulty of solving complex regular constraints. We proposed Raleigh, a preprocessor that transforms these hard string problems into easier integer problems. It does this by reasoning about string equivalent classes. Raleigh dramatically accelerates ACP analysis. It makes analysis practicable for complex real-world scenarios and also enables the verification of policies that were previously untestable. And thank you, and I'm now happy to take your questions.